Hello everyone. I missed the September 13th course class due to my personal reason. So I promised I will record the video and post the recorded video on the YouTube. So now I'm recording the video. So actually this class is the day 5 class. So we will cover the Moore's law and then maybe the part of the instruction set architecture if possible. So okay, so please watch this video and then watch this video before the day 6 class. Okay, because this is the continuous class. Okay. So in the previous class, we covered the power consumption of the computer processor and computer systems. So I mentioned that power consumption is very critical for the computer systems because it's the running cost of the computer systems. So actually, I also mentioned that the goal of the engineering, so this is the goal of engineering, is to improve the performance and reduce the cost of the system. So in the previous class, we uh, learned about the performance metric, so that is related to the performance of systems, of the computer systems. And in the previous class, we also mentioned the power consumption of the computer system. That means the cost of the system. Okay. Then so so this is the equation of the power consumption. Actually, I mentioned that this is the dynamic power consumption of the computer processor. So the power consumption is the dynamic power consumption of the processor is proportional to the capacitive load. That means, so okay, I will use the, where is the, okay, here, I think it's here. Okay, so the power consumption of the processor, so that means the dynamic power consumption, is proportional to the capacitive load. That means the area of the computer chip, and then the square of supply voltage. So that means the VDD to the CPU chips and frequency. So also proportional to the frequency. Okay. Also, this is the very important equation that represent the power consumption of the processor. So you need to remember this equation. Okay. So we learned about the Dennard scaling. Okay. So I mentioned that the scaling of the CMOS processor is to reduce the width of the CMOS transistor channel. Okay. So this is the simplified shape or some diagram of the CMOS transistor device. So, and then I mentioned that this is the channel. So if we reduce the channel width, then the transistor becomes faster. Also, that means that we can reduce the supply voltage. So actually there are many benefits to reduce the channel width of this CMOS transistor. Also, we can reduce the size of the transistors. Okay, so you mentioned that the S is the scaling vector. That means that the channel width of the transistor, the CMOS transistor, is reduced by 1/S. That means the scaling vector S. Then if we scale down the transistor by S, then we can also reduce the size. That means C. The capacitance. That means the C, because the the area of this transistor channel decides the capacitance of the transistor device. Also, we can reduce the VDD and then, but so we can reduce the VDD by 1/S. And then also I mentioned that we can increase the frequency because that means the channel width is reduced, then the electron moves faster to the other side of the transistor. Okay, so we can increase the frequency. So dynamic power is reduced by 1/S squared, and then also the transistor number of transistors in the same area is increased by S squared. So that means that the power density in the same area is maintained. That is the Dennard scaling. So if the Dennard scaling is maintained, we can increase the performance of the processor very easily by reducing the size of the CMOS transistor. But I mentioned that recently the Dennard scaling is not kept because of leakage current. So if we increase the number of transistors in the same area, then this chip will consume more power. Okay, so that means the end of the Dennard scaling. Okay, so because of this power consumption issue, we increase the number of cores. So I mentioned that the core means the individual working processor. Okay, so each core can receive independent instructions, so individual instructions, and then each core can execute these received instructions independently. So the multiprocessor means that in the single chip includes the multiple cores. Okay. So also this trend is caused by the restriction of the uniprocessor performance. So actually the performance of the uniprocessor increases exponentially, but recently the performance of the uniprocessor is saturated. So that's why we cannot increase the performance of the single core processor. So, and then in order to increase also the performance, we can invest the more cores. That is, I said, that is the same to increase the number of workers. Okay. If we increase the number of workers, then we expect that the more workers will have more performance. Okay, so that means that in the same time, more workers will do more work. Okay, that's our expectation, but it's not always true because of some overhead, like a communication overhead. Also, the tasks cannot be parallelized. So, and then due to these many reasons, we cannot increase the performance of this multi-core by the number of cores. Okay. Okay. Also, at the end of the class, I mentioned the benchmark. So benchmark is the selected applications to measure the performance of a processor. So that is the definition of the benchmark. The programs used to measure performance of the processor. So benchmark is selected from the typical application, typical workload. That means that this type, actually the CPU is the general purpose processor, because if we program any applications, then these any applications can be executed by CPU. So there's actually various types of applications can be executed by CPU. So that's why CPU is called general purpose processor. So that means that the CPU will execute various large amount of types of applications. But how can we measure the performance of different CPUs like Intel i5 or AMD Ryzen 5? How can we compare the performance? We need some representative applications that can measure the performance. So we select the typical workload, the typical application from the various types of application, and then we decide we make the benchmark applications. And then one of the most popular benchmarks for the CPU performance is the Spec Benchmark. So recently the Spec 2K17, right? That means actually in this slide mentioned the CPU 2006 is called the 2K6, but recently the Spec 2017 was released. So this is the most recent version. So we used this version of the Spec Benchmark. Okay. So I mentioned the Spec Benchmark is the collection of typical applications. So this table shows the Spec Benchmark applications, and then as you can see, you can find the names of benchmark applications, and then you can find the description of the benchmark, like so perm is the string processing, bzip is the compression, so GCC is the compile application. Okay, so this is a collection of applications. You can, as you can see, you can find some number of instructions or some CPI, and then collect cycle time of some specific processor. Okay, so as you can see, these benchmarks will be executed on the Intel Core i7 process, i7 920. Okay, so that means that this is the benchmark. So this benchmark will be compiled by x86 ISA because Intel used the x86 ISA. Okay, so if this benchmark is compiled, then instructions will be generated from this source code high-level language. Okay, so this is the instruction count by compiled by x86 compiler, and then as I mentioned, the CPI and the clock cycle time is the unique characteristics of CPU. Okay, so this is the Intel Core i7. So this CPU has the i7 architecture, so that means the core architecture, and then this clock cycle time is determined by clock frequency. Okay, so based on the instruction count, CPI, and the clock cycle time, that means the micro architecture of the CPU, then total execution time is measured. Okay, we can just run this compiled application on the Intel CPU, Intel Core i7, and then we can compare with the reference time. So this is the reference execution time of the reference machine. Okay, so that means the baseline machine. So just remember, so just note that when we measure compare the performance of the computer processor, we just compare the execution time, right? So the execution time of this CPU by this CPU is compared by execution time by reference processor. That means the baseline processor. So the spec ratio is calculated for each spec benchmark. That's how we just measure the performance with the spec benchmark. Okay. Another type of benchmark is to measure the power consumption of the computer system. And this benchmark is called the spec power benchmark. So this benchmark is used for measuring the power consumption of the computer system actually. But this spec power benchmark is used for measuring power consumption of server. Okay, and then this spec power benchmark used some different power consumption metric called the SSJ OPS per watt. What does that mean? So watt is the metric of the actually power consumption, and then SSJ underbar OPS means the server side Java operation per second. So that means the number of Java instructions per second. So executed, the number of executed Java operation per second. Okay. And as you can see, in this equation, you can find the, oops, what happened? I don't know why. So you can find this is summation. So I will explain later. So why do you use this summation from I equals 0 to 10 for power and then for the server side Java operation per second? It is because the power consumption of a server is not proportional to the amount of workload executed on the server system. What does that mean? I will show the example. So this is the spec power benchmark, result of the spec power benchmark for Xeon X5650. So this Xeon is the server CPU. So that means that this benchmark is executed on the server system. Okay. So this number number I from 0 to 10 represent the target load on the server system, like 0%, 10%, 20%. Then this is the performance value, like SSJ on the bar OPS. Okay. So as you can see, based on this percentage of a target load is proportional to the performance of a server, because 0 is 0, 10 is 86K, and then 20% is the 176K. Okay, so performance is proportional to the target load, and then that's obvious. But if you see the average power consumption for this target load, if the target load is 0%, then the power consumption is 80 watt. 10%, 121 watt. 100%, 258 watt. So what does that mean? And then, so this is the overall sum of the performance, and then overall sum of the power consumption for this target load from 0 to 100. We just integrate this performance metrics, also integrate the average power metric, and then just divide this integrated performance metric with by the integrated average power metrics. Okay, so this is the result of the spec power benchmark. Okay, so why do we use this metric? Because even though the target load is 0%, this server system consumes power, electric power, like 80 watt. So that means the power consumption of this server system is not proportional to the performance what the target load of the server system. That's why we use this metric for the spec power benchmark. Okay. So if the target load is 100%, the power consumption is the 258 watt. 50%, 170 watt. That is the 66% of this maximum power consumption. Okay, it's 100% load. And then if the target load is the 10%, the power consumption is the 121. That is the 47% of this maximum power. So what is observed? Power is not proportional to load. Load means the amount of work or the performance. Okay, but the load is the more right representation. So power is not proportional to the amount of workload. Okay. So if we get some highest efficiency, if we achieve the highest efficiency on the server system, then we can just maintain the target server load to the 100%, because if the target load is 50%, but the power consumption is just 66% of the maximum power. Okay, so on the cloud, on the server system or some cloud infrastructure, so in order to increase some efficiency of these server systems, then it is required to maintain this amount of workload to some high level, because if this amount of workload is low, then the power efficiency of this server system will be very low. Okay. Okay. So I explained about the power in proportional the server system. Okay. Okay, let's talk about the Moore's law. Actually, this Moore's law Moore's law is very popular because the advance of the semiconductor industry actually actually follow this Moore's law. Okay, so actually the Moore's law is not some theoretical law. This is some empirical observation. So that is just observation actually. So the actual, but the goal of this semiconductor industry is set by Moore's law, because this Moore's law is the kind of observation and then economical law in the semiconductor industry. Okay, but this is very popular law, and then it's actually very important observation in the semiconductor industry. Okay. Okay. So what is Moore's law? The performance or number of transistors will double or triple every 1 year, 18 months, or 2 years. Okay. Well, okay. Let's see the answers. I so this is the Moore's law in the Wikipedia. Okay, so I copied the definition of the Moore's law from the Wikipedia. So Moore's law is just the observation. It's not a theoretical law. So what? The number of transistors in a dense integrated circuit. Okay, number of transistor doubles about every 2 years. That is the Moore's law. Okay, so is that number of transistors double every 2 years. Why is it important? And what does that mean? So actually in the previous class, I mentioned the CMOS scaling. So that means that the size of the CMOS transistor is reduced, is decreased. And then also I explained about the benefit of this CMOS scaling. So with the CMOS scaling, we can also reduce the size of the CMOS transistor. Also, we can increase the performance of processor. Why? The channel length, the channel width is reduced. That means that the CMOS transistor can work faster. Okay. So, but so work fast. So CMOS transistor work faster, so we can reduce the supply voltage and then we can increase the clock frequency easily if we reduce the size of the transistor. Also, the size is reduced, so that means that in the same area, we can include more transistors in the same area. And then this transistor is better transistor, is working faster. So F is increased, but the same number of transistor is included in the unit area. So, and then power density is also maintained. So that means that the power consumption is nearly the same, but so this is the CPU on the 1990, so launched on 1990, and then after 2 years, 92, then by the Moore's law, in the same single chip, the CPU can include the twice of transistors. Okay, the number of transistors doubles, and then the CPU work 2x faster. Not 2x, it's about square root of 2 faster. So it's a better CPU. Okay. Then power density is nearly the same. power consumption is the nearly same. So with the same power consumption, we can get the better CPU. That means the Moore's law. So Moore's law just actually set some goal of the semiconductor industry. What does that mean? So actually the Moore, Gordon Moore, that is the actually the Moore's law was firstly mentioned by Gordon Moore, and then the Gordon Moore was the CEO of the Intel, and then Intel set some goal of this advanced in semiconductor technology based on this Moore's law. Okay, so that means that the semiconductor technology advanced based on the Moore's law. And actually, the Intel set this goal based on this Moore's law, the technology advanced, the goal of the semiconductor manufacturing. Okay, so Intel set this goal, and then based on this goal, Intel developed the semiconductor technology, and then also the CPU process, CPU. Okay, the performance of the CPU, and then also the manufacturing of the CPU. Okay. So let's see how the Moore's law is maintained our past decades. Okay, so in this graph, the y-axis means the transistor count, and then as you can see, this is the log scale, and then x-axis is the years. Okay, it's a time, and then as you can see, the number of transistors by year increases actually exponentially. That's similar to the Moore's law. The number of transistors doubles every 2 years. That means that number of transistors in the single CPU increases exponentially. So that is the Moore's law. So based on the Moore's law, the CPU also advanced. Okay, number of transistors per CPU increases exponentially. But recently, we are facing the end of Moore's law. Why? Because the CMOS scaling is getting more difficult. So and then I believe some of you heard about some struggling of the Intel's semiconductor technology, because the Intel is struggling to the 10 nanometer technology or 10 nanometer technology. And recently the CMOS TSMC used the 7 nanometer or 5 nanometer CMOS technology. So it's some technology node, but currently the Intel struggles to advance to on the 10 nanometer technology node. It's very difficult. So that means the CMOS scaling is getting more difficult. So, and then that means also it's not easy to maintain the Moore's law in the semiconductor components. Okay, let's see the trend. So recent trend on the microprocessor. Let's see the microprocessor trend for 4 years. So as you can see, this y-axis is also the log scale axis. Then this x-axis means the year. That means the time. And then this graph shows the different numbers, like a number of transistors, and then single thread performance, and the frequency, typical power, and the number of logical cores. So the first number of transistors increases exponentially based on the Moore's law. Okay, so it is maintained, but as you can see, the performance of the single thread, that means the performance of uniprocessor is saturated, it's becoming saturated. So that means this is a single core. The performance of a single core is saturated. So that means if our application is compiled and then a single thread is generated from this application, the performance of this application is the nearly same for the processor of 2010 and the processor launched in 2020. If the application is compiled to single thread, okay, because the single thread performance is saturated. And then, as you can see, the frequency is already saturated, like in early 2000. Sorry. But after this, even though the frequency is saturated, the performance is slightly increased because of the effort of computer architect. Okay. And then, as you can see, the typical power is also saturated because this frequency is saturated. The typical power is also saturated. But what is increased? Number of logical cores. So that means from 2000, the middle of 2000, the multiprocessor era started. Okay, so we live in the multiprocessor era, not uniprocessor era. So until the middle of 2000, the computer architect focus on increase the performance of uniprocessor. But after that, they realized that, oh, it's not easy. It's very difficult to increase the performance of a single core because of power consumption. Okay, so and then we cannot increase the frequency of this single core processor because of power. Okay, power consumption. It's not easy to increase the single performance of the single core. We can include more cores to increase the performance of this single CPU chip. Okay, that is the multi-core. So based on the Moore's law, we can increase the number of cores like this. But if the Moore's law is if Moore's law ends, then means that we cannot increase the number of this transistor. Okay, so that means it's not easy to increase the number of logical cores. So what's the answer? How can you increase the performance of CPU? It is very difficult. Okay. So okay, let's see the Moore's law in the theorem. So this graph shows also the x-axis is the time, and then y-axis means the megabits, the number of bits per DRAM. So until the late 1990, so this density increased 1.5 times per year. Okay, and then this trend is reduced to 1.1 times per year after 2010. So this trend shows that it's not easy to scale down this CMOS transistor. Okay. Okay, let's see the Moore's law in Intel processor. So this Okay. This red graph shows the trend of the Moore's law, and then but this blue graph shows the actual number of transistors in Intel processor. So as you can see, so actually the Intel processor, actually the Intel processor cannot keep the Moore's law. Okay, so actually this gap is increasing. So I said we are facing the end of Moore's law. So that means we cannot use better transistors. It's not easy. So actually the Moore's law represents the advance in semiconductor technology. So and also it represents the scaling down of the CMOS transistor. But end of Moore's law means that it's not easy. It's very difficult to scale down the size of the transistor, and then that means it's not easy to make better transistor in the future. But we are facing the end of Moore's law. So the trend is changing. So we need to develop some different we need to develop the CPU in the different direction. Okay, and that means there is end of Moore's law means, and the end of Moore's law teach us. Okay. Okay. So let's see the 8 great ideas. You can find that these 8 great ideas in the textbook. So and actually the computer architects developed the computer processor based on these 8 great ideas. Okay. The first idea is the design for Moore's law. So, so I said that Moore's law is a very important law in the semiconductor technology and CPU industry. Okay, so the first law, actually, the first idea is design for Moore's law. So based on the Moore's law, we set the goal of the advanced in semiconductor technology, and then we develop the CPU or processor technology. So design for Moore's law, and then use abstraction to simplify design. Okay, so abstraction, and then make the third idea. The third great idea is to make the common case fast. It's very important also. Okay, what is the common case? So let us assume that is we use the CPU for actually the 80% of the CPU time for application A, and then let us assume that 5% of CPU time for application type B. And then if we want to improve the performance of the CPU by changing the architecture of the CPU, then we need to focus on the application type A, because we use more time for executing application type A than B. So it's very important. For the application type B, just consume the 5% of the entire execution time of the CPU, and if we improve the performance for this application B, then this performance improvement for this CPU will be very low, because it's just the 5%. It's the maximum performance increase is 5%. Okay, So we need to focus on the common case, not a specific case or specific applications. Okay, we need to focus on the common case. And then performance improvement via parallelism is very also critical. So parallelism means that it's very similar to the multi-core or multi-processor. Okay. And then performance via pipelining. So we will learn about the pipelining in chapter 4. And then performance via prediction, like a branch prediction, where some various type of prediction technologies are applied to the modern CPUs. And then the most popular prediction technique is the branch prediction. Okay. And then hierarchy of memories. So we will learn about the memory hierarchy in chapter 5. Okay. This is also very critical to improve the performance of entire computer systems. And then the 8th idea is the dependability via redundancy. And then it is required for more reliable computer systems. Okay. It is required for the reliability. Okay. So these are the 8 great ideas. And then actually the computer architect or computer processor designer developed these computer processors based on these 8 great ideas. Okay. Okay. Okay, I will conclude the chapter 1. So we need to focus on the cost and performance of a computer processor. Okay. And then we also learn about the abstraction, and then we learn about the instruction set architecture in the chapter 2 actually. But we learned about the various layers on the computer systems like software and hardware. And then we learn about the performance metric, and then in order to compare the performance of 2 different systems, we need to measure the execution time. And then also we learned about the cost of the computer system as the power consumption. Okay. Okay, this is the end of the chapter 1, and then we have still time, so let's move on to chapter 2. So chapter 2 is the title of the chapter 2 is instructions, language of the computer. So in the chapter 2, we will learn about the instructions of processor or instruction set architecture. So in the chapter 1, I briefly explain how our applications are compiled and executed by processor. So actually we write the code using high-level languages such as C or C++. And then these high-level languages are very similar to our natural language or our normal language like English. And then these high-level languages are compiled to the assembly code. And then actually the assembly code is very similar to the machine code, and then also mapped to the one-to-one by machine code. And then this assembly code is translated into machine code. Like these machine codes are composed of binary code like 1 and 0s. And then computers are just receive the instructions one by one, and then based on the definition of this instruction, computer processor just execute some functions. So in order to understand the execution behavior of the computer processor. Also, to understand some architecture of this computer processor, we first need to know about the instructions which will be executed by processor. Okay, so in this chapter 2, we will learn about the instructions of computer processor. Okay, let's see this funny figure. Okay, so this is this is the figure from the computer architecture. So it's the advanced computer architecture textbook, like the computer architecture or quantitative approach, quantitative. Okay, so so can you see? You can see the software and then hardware and then instruction set here. So this figure shows the relation between software, hardware, and instruction set architecture. Okay, the software is software like two people playing on the plate of the instruction set, and then hardware is lifting up the plate of the instruction set. So actually the software, that means the application runs on the hardware. That means the software plays on the hardware, that means the computer system. And then between this software and hardware, there is instruction set. Okay. So that means the instruction set is the interface between software and hardware. But also that means because of this instruction set, the software does not need to understand how hardware works. What does that mean? So this is the application, and then this application is compiled and then generate the instructions like add, sub, like multiply, and branch. Actually, this instruction just define the result of this instruction, like add R1, R2, R3, and then the definition of this add instruction is R1 equal R2 plus R3. So if this instruction is defined, then the computer the hardware, that means the computer processor, can just generate the result of the instructions. Okay, and software do not need to understand how these results are generated by hardware. Okay, so that means the software engineers actually do not know how hardware works. The only important thing is the result of instructions. Okay, if the R1 is correct, then that's okay. Okay, so that is also block, and then software do not see this hardware. The hardware is the same. Actually, the hardware is lifting up the plate of this instruction set. So actually this hardware does not need to understand about the application or the high level software. The hardware, actually the goal of the hardware to generate the correct instructions defined by this instruction set. Okay, so this videos explain the relation between software and hardware and instruction set architecture. Okay. Yeah. And then I will explain the relation of instruction and computer hardware. Okay. So these are the uh, this is the instruction given to the computer processor, and then this is just the black box. So a certain instruction is given to the processor, then processor generates the result, and these results are defined by instruction set architecture. So for example, so add R1, R2, R3, and then the definition of this add instruction is the R1 equal R2 plus R3. Then the processor read the data from the R2 and R3 and then execute the add operation for this data and then generate the result and then store this result to the R1. That is the definition of the instruction, and then based on this definition, the processor generate the result. Then in that case, the result means the change of state. What does that mean? What is this state? The state of the computer processor is the contents of memory devices like main memory, like DRAM or register files. Okay. If a certain data is changed, so that means the change of state. So instruction is given, and then based on the definition of the instruction, the processor change the data. So that means a certain state is changes. So this is the behavior of the computer processor actually. And then this behavior of a computer processor is defined by instruction set architecture. Okay. So in this textbook, we will learn about the RISC type ISA, the instruction set architecture. And then there are different types of ISA like arithmetic logic instructions and data transfer instructions and control instructions. So we will learn about these types of instruction later. And if this instruction is given, then the architectural states, as I said, the data stored in the memory devices are changed. Like add R1, R2, R3. And then in this instruction, the R1, R2, R3 just means the data in registers. Okay, registers. And then based on this instruction, the R1, the data in R1 is changed. How this data is changed? R1 is R2 plus R3. So data is changed and then stored in the register. So that means that this architectural states, there is the data in the memory devices or memory components are changed. Okay. There's the instruction set architecture. So basically the instruction set architecture just define the result of the instruction. Okay. Also, this instruction set architecture also defines the many different parts like number of registers or size of the addresses or size of the data. are also defined by instruction set architecture. But basically, instruction set architecture just defines the behavior of instructions. Okay. So basically, so instruction set architecture is the contract between software and hardware. Okay. These high-level languages applications are translating the instructions. This is the very then these instructions also define some simpler behavior of the computer processor, and then based on this defined instructions, the hardware of the computer processor is designed. Okay, so that's why the instruction set architecture is the contract between software and hardware. Also, as I mentioned, this instruction set architecture also defines the number of registers, then some the address, the width of the memory address, and then some other rules in the inside of the computer processor. Okay. So actually, there are very popular instruction set architecture such as the x86, ARM, and RISC-V. Okay, so these are called the instruction set architecture, like x86, ISA, ARM, ISA. Okay, so x86 ISA processor means that if this processor is designed for x86 ISA, then this processor can execute the instructions defined by x86 ISA. Okay. So for example, this is the Intel CPU. Intel CPU can execute the x86 ISA. How about the AMD? AMD CPU also can execute the instruction set x86 ISA. This is because Intel CPUs or AMD CPUs are designed to execute the x86 ISA. But how about the Exynos? Oops. Exynos cannot execute the x86 ISA because Exynos is designed for executing ARM instruction set architecture. So based on the instruction set architecture, a certain CPUs can execute only a certain instruction set architecture. Okay, but Intel has the many different micro architecture, like core architecture, like Intel i7 and then Intel Celeron, the Intel. Also, if we use the AMD CPUs, AMD has the Ryzen 7 architecture, micro architecture. So micro architecture is different from instruction set architecture. So micro architecture just mentions how the inside of the CPU, how the inside of processor is designed. Okay, that is related to the micro architecture. So this is related to some design of the detailed architecture. Okay, so even though Intel Xeon and Celeron can execute the same binaries, so compiled by x86 ISA, but the microarchitecture is different. So Xeon architecture is different from the Celeron microarchitecture, and then Xeon is more powerful than Celeron. Okay. So microarchitecture also decides the performance of the CPU or processor. So you need to remember that the instruction set architecture is different from microarchitecture of the CPU. Okay. So what is the instruction set? It's the set of instructions. Instruction set. So set of instructions. That means the group of instructions, is a repertoire of instructions. Okay. Just some okay. The instruction set is the set of instructions. Okay. So actually the early computers, early processors just support the simple instruction set, but as the computer processor advances, and then modern processor supports the more instructions. Okay. So instruction is just the repertoire of instructions, the group of instructions. Okay. And then let's think of okay. So actually, in this course, we will focus on the RISC-V instruction set. The RISC-V instruction set is the RISC type instruction set architecture, like the RISC type. And then actually there are two types of instruction architecture. So RISC type, and then CISC type. So RISC type means the reduced instruction set computer actually. And then CISC means the complex instruction set computer. So that means the RISC type instructions are more simpler than CISC type ISR. I think I mentioned simpler. Okay, so that's why the RISC type ISR is called the reduced instruction set computer. Okay, and then we will learn about the RISC-V ISR in this course. So that means, as you can see, this RISC-V includes the RISC in its name. So that means also RISC-V is the RISC type ISR, instruction set architecture. Okay. So this RISC-V ISR is the open source architecture. So and then this RISC-V ISR was developed by UC Berkeley. And then, so actually the author of this textbook is David Patterson, and then David Peros, and then Hennessy. So this is the open ISA. That means that we don't need to pay some royalty if we use this instruction set architecture. So this is different from the ARM ISA. So ARM is also RISC family ISA, but the ARM is not open instruction set architecture. So if we use the ARM ISA, then we need to pay royalty to ARM. So this is the commercial instruction set architecture. x86 is the same. It's not open ISA. So, but RISC-V is different. It's the open ISA. So if we use the RISC-V instruction set architecture, we don't need to pay any royalty to this for using RISC-V ISA. So we can actually, based on this RISC-V ISA, we can we can make any processors. Okay. So actually, so if you have an interest about the RISC-V ISA, then you can see that this slides and then video on this link. Okay. So this slide is from the workshop introductions and the RISC-V update by Asnovich. And also you can watch the video via this link. Okay. And then if you watch this video, then you can know the philosophy of the RISC-V ISA design. Okay. So I need to actually I'm recording this video on the home. Okay, some tablets are not as good as my tablet on my office. So I think I need to stop here, and then I will continue from this slide in the next class. Okay. Thank you for watching, and then see you in the next class. Okay. Bye.